Hello and welcome to Lecture 12 of Math 2R03. In today's lecture, we're going to be looking at Section 3.D of the textbook on invertibility and isomorphisms. And we'll actually spend 2 lectures on this section because there's a lot of good content and that we would like to go through. So I'm going to start with a recap and kind of justify why we would want to look at the notion of invertibility. And then we're going to look at some of the properties of invertibility and finish up today's lecture talking about isomorphisms. So a recap of where we are from last lecture. In the previous lecture, we learned about the matrix associated to a linear map. So remember the setup. We have a basis V1 through Vn for V and a basis W1 through Wm for a vector space W. And we're looking at a linear map from V to W. And the matrix of this linear map is given by an M by N matrix where we're getting information from where we send the kth basis element. Okay, so we look at the kth basis element. It gets sent to something in W. We can write it in terms of the basis of W. So we can rewrite that as A1K W1 plus A2K W2 all the way up to AMK VM. Right, so let's give some names to this stuff. This is the image of VK under the map. And this, what we've done here is it's expressed in the basis of W. And what you want to think of is we have all of these coefficients that show up here, A1K, A2K, all the way down, and that becomes the kth column of the matrix T. So that's what we learned last time. And so what you should realize, and what we talked about in the previous lecture, is in some sense what we're doing is developing kind of a dictionary between linear maps and the material that you would have seen in Math 1B03, which is matrices. Right, so let's make this a little bit more explicit. So once we have a linear map and once you fix a basis, you get a matrix over here. On the other hand, we also know that once you have linear maps, you can take their sum or you can take their scalar multiple. Okay, these are linear maps. And on the other side, this corresponds to taking the sum of the individual the individual matrices. So the matrix associated to the sum is the sum of the matrices, and then the matrix associated to the scalar product of our linear map. So the matrix associated to that is the same thing as first taking the matrix associated to the linear map and multiplying it by the scalar. And we also talked about composition of linear maps, and that would correspond on the other side to matrix multiplication. So on the right-hand side is we're getting things that we would have seen in Math 1B03, and what we're doing in this course in 2R is kind of explaining everything in terms of linear maps. Now, if you think about back to your first linear algebra course, you know, there's another type of matrix that we sometimes are interested in over on this side, right? So on this side, we also have the notion of the inverse of a matrix. So the question then is there something over on this side that we should also expect? Should the inverse of a matrix somehow tell us something about linear maps? And that's really what we're going to be looking at today, is kind of trying to understand what should go into this question mark, this spot that I filled in with question marks. So that's actually what I want to start off by, is actually telling you what we want to put into that spot. Okay. So a linear map T that goes from V to W is invertible if there exists a linear map that goes in the opposite direction, W to V, such that ST is the identity on V. So what does that mean? i.e., if you think of this as a function, on V, when you plug in V, you should be the exact same thing as plugging it into the identity function, and you should get back V for all vectors in V. And when you look at the other way, is you first plug something into W, that gives you something, if you take a W and you first plug it into S, you get something into V, and then you plug it into T to get something back on W. This should be the identity on W. Okay, so i.e., you would expect that if I take any element in W, that should behave the same way as applying the identity element, and you get W for all W in W. Okay, and we'll call a linear map S we say a linear map S is the inverse of T if we have that ST is equal to the identity and TS is equal to the identity. So this linear map is the inverse of T is if it has these two properties. Okay, so we'll pause here in a second, but when we come back, what I want to show is that if a linear map is invertible, because not every linear map is invertible, but if it is invertible, then it has a unique inverse. Okay, so we'll take that up and then we'll talk some more about some of the other properties about when a map is invertible.